Welcome to part 2 of multiple regression. In part 1, we saw how to fit a multiple regression model to a data set. Today, we'll be measuring the fit of that model and checking if that model meets the assumptions for multiple regression. All right, by the end of the video, you'll be familiar with R squared and adjusted R squared, the root mean square error, and be able to check the assumptions. I'll be continuing with the example from the previous video. So this was the grandfather clock data set where we have antique clocks, and we're trying to predict the price or model the price here that they'll fetch at auction based on the age of the clock, x1, and the number of bidders, x2. All right, so this is our model with the parameters in Greek, the beta coefficients, and epsilon for error. So when it comes to measuring the fit of a multiple regression model, we're going to do it in a very similar way as when we measured the fit of a simple linear regression model. So in simple linear regression, remember, we used little r squared to measure the proportion of variation in the y variable that was explained by x. We're pretty much going to do the same thing here, except now it's called the coefficient of multiple determination because we have multiple predictors helping to determine or predict the variability in y. So for multiple regression, we're going to upgrade this to a capital letter R. So this is big R squared. But it would be calculated just like it would in simple linear regression. We would measure the proportion of the unexplained variation by taking the sum of squares for the errors over the sum of squares total. And then 1 minus that would be the proportion that we did successfully explain. So this will be found at the very top of your model output in the summary of fit section. So R squared, point around to 3 decimal places, so 0.893, which represents the 89.3% of the variability in the grandfather clock prices, was explained by this model, which contains now multiple predictors, the age and the number of bidders. Well, you may have noticed, especially when we did simple linear regression, that right under R squared, there's another R squared ADJ, which is short for adjusted. So in multiple regression, we're going to use that one. Actually, we'll use it more than we will the regular R squared. So the thing about the regular R squared is it's always going to increase, or at worst case, stay the same as you include more predictors in the model. So there could be the temptation to, if you had a huge data set with hundreds of predictors, why not use all of them to predict y? That would give you the highest R squared. But with multiple regression, if we're really trying to understand how the world works, maybe 100 predictors is just way too complicated. Maybe we could boil it down to 2 or 3 really important ones. So generally, we're going to favor a simpler model. It's easy to interpret. So the adjusted R squared will help us gauge if we have an appropriate number of predictors relative to the size of our data set. Okay, so the formula for adjusted R squared involves R squared, but it's basically going to penalize it a little bit. So the adjusted R squared will be smaller than the regular R squared. And it's a function of the sample size n. So how many clocks do we have in this example? And then the number of predictors k. All right. So a rule of thumb is that you don't want, or you can kind of fit in about 1 predictor for every 10 observations in your data set. So if we have 20 clocks, we probably wouldn't want to go any higher than 2 predictors. In another data set with 50 observations, we could probably go up to 5. Loose rule of thumb. So let's compare. The adjusted R squared for our clocks was 0.893, just about. And then the adjusted R squared is going to be a little lower, or in some cases a lot lower. Here, it's just a little bit lower, 0.885. So we'd say we just kind of throw that into our interpretation for R squared. So we gave the regular R squared and identify that as the proportion of variation that's explained by our predictors. But we'll also just include the adjusted value as well. So it's really the comparison that's important. We want them to be close. If our regular R squared was 89.3% and our adjusted was way down at, say, 60%, there's a big discrepancy. So that would indicate that you have way too many predictors and you need to trim your model down. But when they're close like this, that's good. That's saying we haven't overloaded our model. All right. So like I'd said, we generally prefer simpler or leaner models with only the really important predictors in them. In video 3 or 4 we'll get to comparing competing models and picking which is the better model. So a few of our criteria would be the R squared, how it compares to the R squared adjusted, and then just kind of generally speaking, fewer predictors is generally favored because they're easy to understand. Another way we might compare two models to see which we think makes the best predictions is with the root mean square error. So we saw this with simple linear regression as well. So this is symbolized S sub E, which tells you, well, what's the typical size of an error from this model? Okay, so error, remember, is how far off was the actual result from the prediction. All right, this will be measured in the same units as Y. So for the clock example, we're modeling the prices in dollars. So our root mean square error is also in dollars. We can say here that the actual prices that these clocks sold for were typically about $132.36 away from what was predicted by the model. Right. And if you look at the prices, they're in the thousands. So usually we're about $132.36 off in our predictions. All right. So if you had multiple models, you would prefer the one with less error. So a smaller root mean square error is good. All right, let's shift now to checking the assumptions for linear regression, multiple linear regression. They're actually the same assumptions as simple linear regression because it's all under this big umbrella of regression. So with simple linear regression, we said that X and Y had to have a linear relationship. Well, now we need each X to have a linear relationship with Y. We also need constant variance. So is the variability in Y constant across X? We need our errors to be independent. We need our errors to be normally distributed. And then, as always, we'd like to have a representative sample of the population. All right, keep in mind, errors and residuals are the same thing. So forgive me if I kind of go back interchangeably, but just think of them as synonyms. Okay, so how would we check that there's a linear relationship between Y and each X? Well, we started doing this in the last video. We made a scatter plot matrix. So here we can visualize the relationships at a glance between all the variables in our study. And for this condition, we're concerned about Y versus each X. So these top two scatter plots on the right, or you could use the bottom row. Either way, they show the relationship with Y. So on each of those plots, we had said in video number 1 that it seems like the relationship is pretty linear. We don't see any curved patterns there. Some folks, if they see basically no correlation, some people will then decide not to include that predictor in the model. I like to keep it in, and we'll have ways of testing later on if it seems to be useful or not. Okay, so the scatter plot matrix is like the very basic way to check for a linear relationship. We have a few more sensitive ways though. So we can do what we did in simple linear regression, which is look at the residual by predicted plot. And as with simple linear regression, we're looking for the linearity condition to make sure that there's no curved patterns on this plot. So down here, I don't see any curved patterns. Definitely no parabolas or hockey stick shapes or anything like that. So this seems all right. Lastly, we could plot the residuals versus each x. Let me go into Jump and show you how to do that. All right, so here's our data set, and I'll remind you for multiple regression, we're going to use analyze fit model, where the thing we're trying to predict is y, and then our predictors, we're going to add all of them down to the model effects and run that. So to save our residuals, oh, I should note, so if you did it this way, and you just scroll down, one of the output items that's produced is the residual by predicted plot. So this is what you saw the screenshot of where I didn't see any curved patterns. All right, I was going to, though, save the residuals. So this window shows the output from our multiple regression model. I'm going to use the very top red triangle, save columns, residuals. Doesn't look like anything happened, but they're now in our data table in a new column. So let's plot those residuals versus each x using a fit y by x. So let's let the residuals be y now. And we want to plot it against age of the clock because that's one of our predictors. We also want to plot it against number of bidders because that's the other predictor. So you can put these two different predictors in as x, and it's going to make two different graphs. All right, so we are looking here for random scatter, no curved patterns. So this one on the left with the age looks awesome, very random. The one on the right, I have had students in the past ask if this maybe looks like a parabola shape. There's so much scatter though. Think about if you added one dot or took away one or two dots, would it change your perception? For instance, where my cursor is, what if we added one dot down here? Then that parabola pattern that some people see would pretty much completely vanish. So if one or 2 points cause you to think there's a pattern, it's probably not a pattern. Right, so it seems reasonable here to treat the relationship between y and each x as linear. If you saw curvature on any of those things, that doesn't mean that you can't do regression. It just means you'd need to make some modifications. So a potential remedy would be to apply a transformation to one or both of your variables that have that curvilinear relationship. Or you could use a technique called polynomial regression, which usually I cover due to our extended spring break, though. That is one topic I'm going to cut from the syllabus this semester, spring 2020. Right, our next condition that we need to check is that the errors are independent. And the only way we can really check is if they're independent over time. So provided that our data table is listed in the order that the measurements were collected, we can make a residual by row plot. So remember, like in simple linear regression, this method isn't going to work if the data has been sorted. So if you notice in your data table, any of the x's or the y is either ascending or descending order, you just can't check. All right, so from my multiple regression output window, I'm going to the top red triangle, down to row diagnostics. And I'm going to add in plot residual by row. In simple linear regression, JUMP automatically connected these with red lines. And remember, we were looking then for a zigzag pattern that just looked like random up and down. Here they're not connected, but we can still think about, well, what it would look like if they were. And here it looks like they would pretty much be bouncing all over the place. So random scatter here is good. It indicates that our errors are not correlated in any way. Because that would violate the assumption. If we saw an ascending trend, that would indicate that there's a positive correlation between our errors, or if there seemed to be a downward trend, then there'd be a negative correlation. So pretty much flat across in a random fashion means they're not correlated. All right, next, are errors normally distributed? So we just saved them, the residuals or errors, into a new column. So we can plot that column and see what it looks like. We've done this a million times, so I'm not going to go back and jump. Here are some screenshots. Now, for this condition, this data set is not amazing. So look at our histogram. It looks kind of bimodal to me. Now, the box plot on its own looks great, but remember that can conceal different peaks. So it looks like there might be two peaks here. And as such, our normal quantile plot exhibits a bit of that heavy-tailed pattern. We don't have as much in the middle as we should. There's this gap on our histogram here under the red fitted curve. And then we have a little too much out at the ends. All right, so for multiple regression, usually we're not going to perform a Shapiro-Wilk test. Usually we'll just look at these graphs, and if it looks reasonably bell-shaped on the histogram and the normal quantile plot looks pretty linear, then we'll just say we're good to go. But this one, being that it's kind of suspicious, I did run a Shapiro-Wilk test, and the p-value is below 0.25. So this is indicating that, yeah, maybe normality is not such a great assumption here. So we're going to find that there's actually a solution to this dilemma. We're not going to be ready for that until about video 4 or 5, though. So let's just keep going, but we're gonna improve on this model later. Okay, so that's it. A short one today. We looked at R squared and how it relates to the adjusted R squared. We saw the root mean square error and what that might tell us about the fit of our model. And then we went through how to check assumptions on the grandfather clock example. So stay tuned. In video number 3, we're going to be testing which predictors are useful.